So today's lecture, I do not know who else is going to come, and I do not know what you would think about it. But technically, this is the main thing, which made this lecture such a mixture of being boring and important. I don't know what actually more of what. Still today, I will have to put my attention to the importance. You know, this theory, it is called Lie theory, however you call it. It actually was created, maybe 101% of it, maybe even slightly more, was created by Élie Cartan. Certainly there is the main theorem. It is not the main theorem from the point of the theory, main technical theorem, the only theorem which you need to prove. All the rest follows from it immediately. And this theorem is called the Cartan criterion. So today's lecture, I will make several statements and also proofs. Certainly, I do hope that what I will be able to say today about the proofs will be sufficient. Who knows? I have my notes just in case, just not to confuse the notations. Yes. At the beginning, yes. No, it is not. The beginning is here. So it is about the killing forms. Do you still remember what the killing form is? There is a more general definition and a more particular definition. More general definition is that you have a Lie algebra, whatever it is, over what? Over, well, field of characteristic 0, R or C from in our perspective. Then, so we have a representation rho, and then you form a symmetric bilinear form over your field that is real or complex under the algebra, which depends on this representation rho. And the definition, the main definition, is, the notation is B rho, and the value of this onto element of the Lie algebra is the trace of the composition rho of eta. So let us establish what actually we also already know about this. This definitely is a bilinear form. Then there is an invariance property, which is immediately proved. B rho of xi zeta eta equals B rho of xi zeta eta. Very easy to prove. I proved it, but this is the main property of this invariance property. Then the next thing, which is less important, but still, the main case for this B rho is the case when B rho is actually, when rho actually is the adjoint representation. So if rho adjoint representation, then the form B add denoted simply as B, denoted simply as B sub G, which is the algebra. So this again is a form, a bilinear symmetric form on the Lie algebra, sort of this invariance hold, but it may be slightly, very slightly extended. Because actually, for this particular form, if you have an arbitrary derivation in G, then you can write that B rho big C eta, not rho, B at BG is equal to BG C minus d eta. If your derivation is an inner derivation, then it is the same as before. For outer derivations, it is a special property of this form. I'm not 100% sure that we will ever need it, but actually the proof is immediate. Oh, you don't see it. I can try to erase it. But if I erase it, you will lose. I don't know what to do. Yes. We use both possibilities. Sit here. So, of the immediate properties, there are two which should be marked. And probably I mentioned both or one. So the first one, that as soon as you have a bilinear, no, I prefer to use the other half of the board. As soon as you have a symmetric bilinear form, I should say bilinear form, symmetric or not, you have the orthogonality, orthogonal complements. And the fact is that if H is an ideal, then the orthogonal complement is also an ideal. This fact follows immediately from the invariance. If you really prefer, I can show this to you. So imagine that eta belongs to H orthogonal, which means that this is 0 for any zeta in H, right? Now I want to prove that if C is in G, then C eta also belongs to H orthogonal. We should prove immediately, because this means, for what we need, that B C eta zeta, again zeta is in H, is 0. But this, you know, is the same as B C zeta eta is 0. No, xi zeta, yes, xi eta, no, so xi, right. What is in H? In H is zeta. So this means that xi eta, no, zeta, xi zeta is 0, right? Yes. And this belongs also to H because H is ideal. This should be 0. So this is an immediate fact. Immediate number 1. Immediate 2 is more immediate. It is the following, that suppose that you have a Lie algebra, G, and an ideal H. Then both are Lie algebra. So there is a form of BG on G, and there is a form of form B eta on eta. And I want to say BH on H, excuse me. So, statement. I will need this at some moment technically. If H is an ideal, then B sub H, it is bilinear form on H, is the restriction to H of the form on eta, on G. You can reformulate it in terms of representations, also will be true, but I will need precisely this fact to understand the statement. So why? What is actually G and H after all? An algebra and ideal, right? So when we use when it takes a basis in G, and the trace doesn't depend on the basis. I first can take a basis in H, and then all the rest, right? Then the matrix of the algebraic representation is a commutator. So if eta belongs to H, then the commuting with eta, it's matrix. It will be like this, because the commutator of eta with anything again belongs to eta. You understand? The matrix has this form. Now I don't know what you think of the trace of product of these two matrices. What is the trace of product of matrices after all? You should take an entry here and a symmetric entry here. Take the product and take the sum. Yes, but in this case, certainly we should take only the entries here. Otherwise, this product will involve a zero and will be a zero, right? This is precisely what I said. So this is equal to the trace of these smaller matrices, which precisely is what I said. Yes, I'm glad that probably I will not need to say anything more about this. And now, yes.
I know we're not supposed to ask about Lie groups, but is there a meaning to the Killing form in terms of Lie group?
You know what? Killing form is a form on Lie algebra. But Lie algebra, as some people know, is a tangent space to the Lie group. Then you can expand this by translations, left translations, and you will get actually a tensor field on a Lie group. You have a temptation to say that this is a metric. What is the Riemannian metric after all? Excuse me for those who are not interested in Riemannian geometry. But what is Riemannian metric after all? This is precisely this thing, that for every point on a manifold you have a bilinear form on the however, in the you also suppose that killing in the real, in the complex case, no signature. But in the real case, but in the complex case, you can feel free to choose if your Lie algebra is simplification of complex algebra, complex real algebra. You can choose real and imaginary part of this form. No speaking of that. You have a bilinear form, symmetric bilinear form, but it's not always positive definite. No, what I said, it's never positive definite. But it may be negative definite, which is more or less the same because it can take minus. If it is negative definite, it is negative definite precisely when the real group is compact. Then one parameter subgroups are geodesics, and the whole geometry is here. If, however, the group is not compact, then this form cannot be either positive or it is never positive, it may be negative definite, but it's not definite at all. And then you have a pseudo-Riemannian geometry with all properties, and geodesics are still, and one parameter subgroup are still geodesics, but the geometry is, well, so there is light cone, but all these things which come which appear when you consider, well, pseudo-Riemannian geometry. So certainly, yes, it is reasonable to consider this. It is not differential form; it's symmetric, not symmetric, symmetric form on a Lie group, and in the geometry of Lie groups, it is always it is considered a lot. But thank you for your question. Now I will formulate 4 main theorems in this theory. And then we will discuss proofs. Of these 4 theorems, theorem 1 will be trivial. It will have a proof immediately. Theorem 2 is the most difficult part of everything. It's called Cartan criterion, and the proof of it is sort of longer, although it involves only elementary linear algebra. Theorem 3, we will prove it partially. You will prove using certainly theorem 2. But this is a part which we really need. Certain equality, we will replace it by an inclusion. One side inclusion, and the second side may be regarded as an exercise. And theorem 4, which is also called the Cartan criterion, is an immediate consequence of the previous theorem. So actually only one serious proof in this theory. And this is the proof of Cartan criterion. From my point of view, maybe you will disagree. Certainly the proof is elementary and belongs totally to linear algebra. But from the point of linear algebra, it is from my point of view, it is not very much usual. In linear algebra, you not too often use such tricks. It's very short. Maybe I will comment after you have the proof, because you can see from in historical perspective connection to others, which were done more or less at the same time. But I am not sure that they were really connected then. So, 4 main theorems. I prefer to have them before my eyes, simply not to confuse the notations. It is formulated for representations. Mostly we will use it for the joint representation. So let rho be a representation. Well, complex or real is not important. And suppose that there is for some ideal n in G, the restriction of rho to n is nilpotent. That is, the operator made produced by any element of n is an nilpotent operator in V. Then belongs to the kernel rho, to the kernel between B rho, meaning that B rho and everything is 0. It follows from this. By the way, I didn't say this to you. Kernel B rho is an ideal because it is the orthogonal complement to 0. Orthogonal complement to any ideal is an ideal. 0 is an ideal. Difficult to disagree. And kernel B rho, by definition, is the orthogonal complement to 0. So it is an ideal. This is a fact. An immediate corollary is that if G is nilpotent, then the form is totally 0. You see? The form on G is orthogonal to G. What else? So for nilpotent Lie algebra, Killing form is totally 0. It follows from the theorem. The theorem is simple. Now I will consider the proofs, but let me first give all statements, including the corollaries. Now theorem 2. Suppose I can become a representation. Then the image of this representation, it is in GOV, is solvable if and only if G prime, the commutative subalgebra, belongs to the kernel B G. This is the theorem, meaning that for solvability we need just this thing, that any element of G prime, any commutator actually in G, has zero commutator, is orthogonal to everything. From this, it is interesting to have these two statements written next to each other, because from this it follows that if Bg is 0, then G is solvable. Please feel free to compare these two statements. Bg is 0 is some property between nilpotency and solvability. Nilpotent algebras are solvable. Yes. And Bg is 0 is something between. Actually, not consulting with any of these two. As I already said, this technically is the main statement. And its proof involves some linear algebra. I will return to it. Theorem 3. It is about the radical. Just to remember what it is the maximal solvable ideal in G. It is equal to G prime orthogonal. Such a strange thing that these two things, radical and G prime, they are precisely orthogonal to each other. As I said, of this theorem, I will prove only 1/2, which I will need. I will not need this theorem in full. And I will prove that the radical. So this is what I am going to. I prove that the radical is contained. Contains. Is contained, yes. The inclusion is the opposite direction. Listed here as exercise in my notes. And I promise that I will never use it. So this is known fact. And then theorem 4. G is semi-simple if and only if Bg is non-degenerate. Theorems 2 and 4 are called both called Cartan criteria. Theorem 2 is actually technically the theorem which we need to prove. All the rest, I will begin with this now. All the rest I will show to you immediately. I mean theorem 1, and then how to deduce theorems 3 and 4 from theorems 1 and 2. And then we will pass to theorem 2, Cartan criteria. It is very interesting what you will say about this proof. It is sort of elementary and unusual. But first, so proof of theorem 1. Nilpotent. This means certainly that Engel's theorem can be applied to it. If so, we have the following. We have V, which is Vm, contains, I write not equal, It's not important. Yes, not important, yes. V minus 1, V0. And any element of eta takes every V to the previous V. So rho n of Vi is contained in Vi minus 1. What of that? By the way, I could do it maybe next moment, but I prefer to say it now. Certainly, we can at every step take V the smallest possible. So it is not necessary, but This means in particular that H radical contains any solvable subalgebra. So this is all. Again, nothing actually. Now the main thing, as I often say in such cases, it seems unfair that this result, which in some sense, maybe if you ask somebody to meant to give the most important, most famous, theorem in the theory of real algebras, probably this will be the result. Semi-simple algebras have, algebra semi-simple is the same as Killing form is non-degenerate. And it becomes such an easy thing after we have all the rest. So it's theorem 4. Proof. Again, let me just not confuse the notation. Two directions. In one direction it's trivial. If G is semi-simple, then is this definition. The radical of G is 0. And then we have that so the theory, the Cartan criterion says that the previous theorem says that then the yes this belongs to kernel of BG. This just kernel BG is 0. Because actually the orthogonal complement to this contains orthogonal complement to 0. The orthogonal complement to 0 is kernel BG. So this implies this contains the orthogonal complement to the radical, which is 0. So we get this. So if G is semi-simple, simply because no solvable subalgebra radical is 0, immediately follows from this that kernel BG is 0. And in the opposite direction, if this is 0, then, according to the first theorem, the nilpotent radical of G is 0. Well, because kernel BG is 0 means that means precisely this. So if this is 0, then this is from our corollary. This is 0, and the nilpotent radical should be contained in this. So it is contained in 0. This means that the smaller algebra, the commutator subalgebra of radical, which is contained in this, is also 0. This means that the radical is commutative. Prime is 0 commutative. That means this is nilpotent. And hence it is contained in an nilpotent radical, and hence it is equal to 0. So radical is 0. This is the chain of implications. Radical 0, prime is 0. So this is commutative. Commutative means nilpotent in particular. Nilpotent is contained in nilpotent radical. Nilpotent radical was 0. Yes, so what I want to say is that everything we get basically for nothing if somehow we settle our relationships with the Cartan criterion. Anything to say at this moment? If you don't have to say anything. say the main thing. I have 12 more minutes. Probably it will be not sufficient to, then I will have to finish the proof next time. But now I will, let's discuss some very much elementary theorems from the linear algebra. First, so forget all this linear algebra, all this stuff. We have precisely what people study in linear algebra, namely a vector space. Let's be complex, I don't mind, and a linear endomorphism. Then the following is true, and I want to know how much you are inclined to believe. There are two operators, S and N. The letter S is the first letter that was semi-simple, which actually means diagonalizable. Letter N is the first, as you can easily guess, the first letter of the word nilpotent. So there are semi-simple and nilpotent operators. Semi-simple means diagonalizable, nilpotent means nilpotent. They commute with each other. And this is all, but also this is unique. So there exists a unique decomposition of an absolutely arbitrary linear operator in V. V is finite dimensional. Two parts determined by F uniquely. By F, provided that they have these properties. S is diagonalizable, N is nilpotent, and they commute with each other. If you give this question to your students of a linear algebra class, do you think they will be able to do this? For this purpose, actually, to give this partial answer, you probably need to know the Jordan normal form. Uniqueness question remains, but all the rest follows from it. If you, so in the complex case, there are blocks. Lambda here, something here, and here. Sometimes people use the low triangular notation. Actually, this upper part also has some shape. Actually, ones or zeros in the next diagonal, but it's not important for me. This immediately shows how to make this decomposition. Because you take this Jordan normal form, you take this diagonal part, and you take all the rest. Diagonal part will be diagonal, all the rest will be nilpotent. Right? The fact that they commute with each other within this block, the operator is lambda times the identity plus n. Lambda times the identity matrix plus some nilpotent matrix. And I personally think that lambda times the identity commutes with everything, in particular with n. Uniqueness, well, written in my, or maybe not, maybe in my notes it's written that it's obvious. It is obvious. It is, what I want to insert, it will be in the new version of my notes. What I want to insert is the fact that it's also true in the real case. What do you think about that? It is easier to, I will formulate and maybe prove two lemmas, and probably this is all for today. Also linear algebra, but everything will be linear algebra. Certainly from one of these lemmas it follows more immediately than without it. I mean, the same is true in the real case. Every operator is the sum of two. One. When I say diagonalizable, you should not, it is diagonalizable certainly over complex numbers, because eigenvalues may be not real. It's okay. And nilpotent is nilpotent. So it's true in the real case. I will use it only in the complex case, but as an exercise you can think about this. Now to theorems, of which actually the first is very much characteristic. Two lemmas. The first is very much characteristic for the whole theory. How these things are related. Suppose that you do have this F. How to find S? And the statement is that actually, well, so for a fixed pair, F and S, F is fixed, S is S from this theorem, then the following is true. It is lemma. There exists a polynomial of one variable. Without the constant term, such that P of F is S. Very much has a set characteristic for this, the whole thing. If of two operators, one is a polynomial of the other one, then these operators are very much similar. Cartan used the word replica. This is the first example of replicas. They're very different. F is arbitrary, S is semi-simple, but still they have a lot in common, and we will use it. The technical reason why they have so much in common is this, that actually S is a polynomial of F. Yes, I think that maybe the best thing I can do now is to present the proof, because it's very short. How to find this polynomial? Again, it is not the same polynomial for all F's. This polynomial is constructed where you have F and you have S. As you have if you have F. So how to do that? We don't know P. But still, this mysterious P can be applied to F, and P is S plus N. Then the usual formula, binomial formula, however you call it, shows that this is equal to P of S plus P prime of Sn plus P double prime of Sn squared over 2 plus so on, right? It is finite because n is nilpotent, then it stops somewhere. Because n to some power is 0. Now S, you can choose appropriate base as diagonal matrix. What do you think happens if you apply a polynomial function, a polynomial, to diagonal matrix? I personally think that simply you apply this polynomial to every diagonal entry, right? Agree? So you have a diagonal matrix, you apply P, and you simply apply P to every. Yes. Now what do I want to do? I prefer to find such a polynomial P, that P of S is S, P prime of S is 0, P K of S is 0. How to achieve this? S has eigenvalues, right? For this, is equal to S, excuse me. For this, I want that P of lambda I is lambda I for every I. For this, I want that P prime of lambda I, P K of lambda I, all are zeros. Certainly, you can find such a polynomial, so you understand. We have the values at several finitely many points, which happen to be equal to the arguments, it's not important, and the derivatives, which happen to be 0, not important. If you take any finite set of points and request that this polynomial and such derivatives take such and such value at this point, that's okay. No problem. So you find the polynomial P with this property, and from this you have that this is equal to S. Very simple. Very common thing in this. I will formulate and maybe even prove one more lemma, after which we have the main lemma for Cartan criterion. And this, the proof may seem strange to you, but still it's very convincing. So, every linear operator in every space has semi-simple part and nilpotent part. And it is well defined, S and N. S is semi-simple, N is nilpotent, and they commute with each other. Suppose we have this F, and also we consider the adjoint commuting with F. So this is we consider the set of all space of all linear transformations in OV, and commuting with. It's also a linear operator, and it also has semi-simple and nilpotent part. So far nothing, but something. Semi-simple and nilpotent part of add F is add S and add N. So you don't need to look. Follows from the uniqueness. What do we want from these operators? Add S and add N. Add S is diagonalizable, but it is diagonalizable because the commutator of so you have an element the diagonal matrix. Right? This is S. Then you have EIG. EIG is a basic element here, the matrix with only one zero entry. And this is lambda G minus lambda I, EIG, which can be checked in 1 second. If you take the commutator of the diagonal matrix with the matrix with only one entry, you have this. So this basis, in this basis, the operator as C is diagonal. If N is nilpotent, that N is nilpotent. We use this million of times. If S and N commute, then add S and add N commute. Add is representation. We also sort of know it. So this is obvious but very important. That actually, when you pass from V to the space of endomorphism of V to GLV, then simply you apply the same operations to nilpotent and semi-simple parts of F. This is lemma 2. Next statement is the main lemma, which I will not formulate because the formulation is sort of long, and now I have minus only negative 2 minutes, which is definitely not sufficient. So I will continue next time.